by introduction, then we'll follow up by what is convolution and why we are using it, and then we'll explain what is the pooling layer and the other layer of the convolution neural network, and then we'll talk about the parameter sharing and sparse connectivity, and then we'll take a look about its architecture. So what is convolution neural network? So in deep learning, a convolution neural network, or sometimes we refer it as a CNN or ConvNet, it's a class of it's a class of artificial neural network, most commonly applied to analyze virtual images. CNNs, also known as a shift invariant or a sparse invariant artificial neural network, based on the shared word architecture of the convolution kernels or filter that slides along input features and provide translate equivariant response nodes as a feature maps. So this definition was from Wikipedia. So, in more general, convolution neural network is a deep learning algorithm which can take an input image, assign importance, learnable weights, and bias to various aspects objects in the image, and be able to differentiate one from the other. So, a convolution neural network will take an image as an input, and then we'll assign an importance, learnable weights, and bias to various aspects or objects in this image, and to be able to differentiate from one to other. So vision is more than the ability to recognize an image, but also understanding where the objects are in the scene. Okay, so we want to build an algorithm that can identify these objects. For example, focus on the yellow car more than, for example, than focusing on this black car. Or for example, we are seeing like there's a people who's crossing this crosswalk. You may want to focus more on them. Or for example, want to focus on this white truck or in this like small bus. So I want to build a convolution neural network that can differentiate or tell us how we can like identify these objects in the image. So we want to talk about a little bit about artificial neural networks. So artificial neural networks, also known as ANNs, it's a subset of machine learning. It is the heart of deep learning. It's very powerful and can handle large and complex machine learning tasks like classifying millions of images or recognizing speech or face recognition or image processing by feeding a large number of images as an input and train this neural network on these images and these train. So we're gonna feed our neural network by a large number of images as an input and train this neural network on this image and on these multiple hidden layers. So we'll take inputs here as input layers and we'll train this models on these hidden layers, on these multiple hidden layers, and by most of our model will be able to learnable and discover these images and patterns in the future. Okay, we can see that artificial neural network consists of multiple layers containing an input layer, as you can see here, and one or more hidden layers, and like an output layers. Okay, each node is, and we can see that each node is connected to another node, and that's used to activate this node as well. Okay, so to specify which value will be passed to the next layer of the network, we have to activate which one of these nodes we are gonna use. Okay, so we have this figure on the right. So a typical layer of convolution neural network consists of input layer and convolution layer and for example a nonlinearity function like ReLU for example, and then we have to apply this output to the Boolean layer. Okay, and we're gonna repeat it several times. So in the first stage the layer performs several convolutions, okay, in parallel, to produce a set of linear activations. In the second stage, each linear activation is run through a nonlinear activation function, like such as ReLU activation function. Okay, this stage sometimes called a detector stage. In the third stage, we use a Boolean layer, Boolean function, so to modify the output of the layer, furthermore like max or min Boolean. So what is the components of your convolution neural networks? We say we have convolution layer, we have Boolean layer, we have fully connected layer, and we have activation function. Okay, but the question now is, what is the best way to combine them? What is the best way to combine these layers? So let's take a look at this image. So we're gonna start by feeding our network by an image. Okay, as you can see, we have here an image of number 2, and this has a dimension 28 by 28 by 1. So we take this input and we feed it into our first layer. So the first layer, it's gonna be the convolution layer. So we feed it in the first layer convolution layer, in the convolution layer, and start doing some calculations. It's known as convolution, and then we have to do like, for example, a non-linear function like ReLU. Sometimes you assume that the activation function like ReLU and convolution are in one layer. Okay, after that we have to take the output and feed it into a max Boolean, and we will repeat that several times until we get sorry, but because I had corona, so I stay coughing. Yeah, so we'll feed our convolution output to our max Boolean and repeat that several times, and after that we'll take this output and feed it into a fully connected neural network. Okay, so sometimes we're gonna use a softmax, and then we'll take the output. So we'll take the output and like a probability. For example, 0 it has like 10% probability, and like for example 1 has like 30% probability, and 2 it has like 75% probability. So we'll choose one that has the highest probability. In this case it's 2. Okay, so now let's start what the convolution operation is. Okay, convolution operation is a fairly simple operation. It's very simple. You start with a kernel, which is simply a small, okay, or maybe just like before we go deep into it, just let's talk about it. So convolution can be defined as an operation performed on two functions of a real value argument. So we can define convolution operation as it's a function x of t star w of t. Okay, where function x is the input and a, so it's equal to, it's an integration from 0 to t between function x of a multiplied by w t minus a to dA. So where function is x is the input and a is a dummy variable of the integration, and w is the kernel, provide an output that expresses how the shape of one is modified by another. Okay, so without going more into mathematical details, let's go and see how convolution works. So the idea of convolution operation, like what we said before, it's fairly simple operation. You start with a kernel, which is simply a small matrix, as we can see here. Okay, we'll start with our kernel, which is a small matrix here, and it's simply a small matrix of weights. Okay, so performing an element-wise multiplication with a part of the input. So we'll take, like, for example, the first part of this input and apply element-wise multiplication, take the second one, the third one, and so on. Okay, and then summing up the results into a single output pixel, so we take a weighted average. Okay, so for example, let's take an example here. So we have a kernel W, and we have a known kernel which it has W, X, Y, Z, and we have our first input which is A, B, E, F. So how we are gonna do, or what we are gonna do here? So we will to multiply our kernel. We were gonna do element-wise multiplication by the input. So we will multiply W by A, we will get AW, and multiply X by B, we'll get BX, and multiply E with Y, we'll get AY, and multiply F by Z, and we'll get FZ. So, and then in the end, we're gonna sum them up and write this value here. Okay, and we'll do it. So like what we said before, what convolution is. Convolution, it's like we have an input image. Okay, we change this image to a bit, like for example 1 0, and we have our filter, it has weights. Okay, so we have this image, and we're gonna start like just multiply and sum them up and write them here. Okay, so for example, like 1 by 1, 1 by 0, 0 by 1, and so on, and then we'll take the summation. Okay, maybe we can just go back a little bit. How should we define the convolution operation? Let's think we have a function of x of t, okay, and w of t. Okay, there's a couple different way you could combine them. For example, you can take xt and then you could add it to the wt, okay, function, or you could take the function x of t and multiply it by w of t. Okay, or there's a third way that we are gonna use it today, which is the convolution. So what I'm gonna give here is a third way that I could combine function. It's called convolution. We denote it by with a star, as we can see here. Okay, so this notation, it's a convolution of the function xt with wt. Okay, this star that I have here, it's not the same thing as multiplication. Yeah, this is a new operation, sometimes a new, that takes two different functions and combine them to give a third function, like what we saw here. Okay, then we will start with the Boolean layer. So Boolean layer is the third stage of the convolution neural network. So we can say it's after convolution and the ReLU operation, or the nonlinear function. Okay, so Boolean is an operation that's commonly used to reduce the dimensional reduction. We use it to reduce the dimensional reduction of our input, reduce like the width and the height, for example, and of our feature maps, while still preserving spatial invariance. Okay, a Boolean function replaces the output. So how it works? So the Boolean function will replace the outputs of the networks at a certain location with a similar statistics of the nearby outputs. For example, like max Boolean will take the max number, or mean Boolean will take the average. Okay, so to provide us an approach to downsampling features maps by summarizing the feature and keeping the important features without such finer details. Okay, so they may not be useful for our task, so we didn't need to keep them, so we just will keep the most relevant features, or the most important features. So one type technique, or a common type technique and of Boolean is and very widely used, so in practice it's called max Boolean. Okay, what is max Boolean? Max Boolean is a very simple and intuitive technique. So it simply will take the maximum over a multiplied by b filters. Okay, b filters size in our batch, and then we're gonna slide that batch. Just move it like over the input, to the first input, to the second input, to the third input, like what we did in the convolution. Okay, so it means that your network outputs at a specific location are replaced by providing a statistics that summarize the nearby outputs. Okay, so it's very similar to convolution, but instead of applying an element-wise multiplication and summation, we are simply going to take the maximum out of each batch, or for example the mean, or yeah, and many other techniques. So let's talk about this max pooling. So we have this input, and we are taking our filter size. It's just like it has like 2 by 2 filter. Okay, so if we have now this image, let's say for example we have 7387, and we'll take the max, so we'll compare which one is bigger. So we have like 7738. Is 3 bigger than 7? No, so we'll take 7. Now we'll compare, is 7 equal than 7? No, they are equal. Bigger than 7? No, they are equal. And now lastly we'll compare it with 8. So yeah, we'll take the maximum number of each input and do it, apply it here. Okay. Another very common alternative technique, it's what is called mean pooling, which will take the average over our filter. So here, instead of taking the maximum number, we're gonna take the average of our filter. Okay, by taking the average, we can represent very smooth way to perform the pooling operation, because you are not just taking the maximum, which can be like for example subject for outliers. Maybe it will have something like very high outliers that has very high value, so we don't need to take these outliers, for example. But yeah, instead of taking the maximum, we're gonna just averaging it as well. Okay. And yeah, by using the pooling layer, we'll be able to shrink or subsample the input image. As what we seen before, we're gonna do like downsampling. Okay, and by that we'll be able to reduce the number of parameters. Okay, therefore we will reduce the computational loads. By reducing the number of parameters, we will be able to reduce the computational load and the memory usage. Okay, and by that we'll be able to reduce the risk of overfitting. So unlike convolution layer, we do not assign weights here. We didn't have any ones, so we just simply take like the average, mean, pooling, or the max before an input. Okay, so all we do is aggregate the input using aggregate functions such as max or mean pooling. Okay, so here there's an example. So here we are doing downsampling operation along the spatial dimension. So let's take a look. Here we have this for example image as an input. It has dimension 224 by 224 by 64. So after applying pooling, we're gonna do like downsampling, and our output will be like, as you can see, it's like almost or like equal half of this image. So we were able to like decrease its size, to downsample its size from 224 to 112. Okay, yeah, so here we have something that is called invariances. So what is that? In this example, we have collection of 3 learned filters. Okay, as we can see, this one, first one, second one, third one. Okay, we have a collection of 3 learned filters. Each one of them contains different versions of rotated 5. As we can see here, look at the 5 here, it's different than the 5 here, and it's different. For example, we rotate it by like 180, rotate by like 270, and so on. Okay, regardless of how its rotation, without caring about its rotation, one of these filters will be activated and match the input and cause a large response in the detector unit. So after feeding this input, one of these one one of these filters will be activated and match this input. For example, it will be match this one, and then it will large response. It will cause a large response in detector. So it will be in detector unit 1. And in the other case, we have this one here. So after feeding this 5, we will like we'll get a large response in detector unit 3 in this one. So now let's talk about pooling and downsampling, like what we said before. So we can use pooling, like what we said before, to get downsampling effects where the output maps has a smaller spatial extent than the input map. Okay, so for example, we can do that by having a stride between poles of two. Okay, for example, what does that mean, stride? So we'll take like just, we are here now, and then we'll take two steps. So we'll just take in the first input we'll take just two, and then we have to move two as well. So if in the first time we'll take 1 and 0 1, and it will take the maximum number of them, so which is 1. And secondly, we'll move and like take the, for the second one we have like here 0.2 and 1, 0.1, and so on. Okay, so as a result we are able to reduce the representation size by a factor of 2, which eases the workload on the subsequent layer. Okay, so parameter sharing. So the other key idea behind convolution neural network is the idea of parameter sharing. So in traditional neural network, like what we said before, like what we see before, we have different values at every row and every column. Okay, we have different value at every row and every column. There is no sharing parameters at all. Every parameter is used exactly once, only one time. While in convolution neural network, in contrast, we reuse each parameter at every position in the input. Okay, so for example, let's say we have like this image here, we have no parameter sharing. As we can see here, like we have like these input layers, and they are feeding, for example, for these hidden layers as. So we have the first one is x3. So x3 is like it's feeding s3. So we can observe that each parameter only appears exactly in one place. So as we can see, it's only appear exactly in one place. So no one of them have the same parameter. Okay, and no one of other input has shared this parameter, so no one has shared the x3 parameter here, this value. Okay, so there's no parameter sharing in this model. And yeah, so like what we said before, parameter sharing, it refers to the idea of using the same parameter for several functions in the model. So as we can see here in this image, we have parameter sharing. We can see that we have reused this parameter several times for the first hidden layer, second one, till like the fifth layer. So as you can see, we use it very many times. Okay, so this black arrow in this graph represent a single parameters that, as a result of parameter sharing, this single parameter was repeated at every single place. As we can see here, it was repeated here, and it was repeated here in the second one, third one, fourth one, and so on. Okay, so it was repeated at every single place in our input space. So so this can be useful, for example, if we build a kernel that looks for edge. Okay, and we only learn about detecting an edge once, and then we can apply that edge detector everywhere, rather than learning, for example, separate set of parameters like for each edge. So parameter sharing, in conclusion, by using parameter sharing, we will simply learn one set of parameters then, rather than learning different sets for each location, and we don't need to store many different parameters because we can use the same parameters in many different locations. Okay, so like what we see before here. And yeah, different parameters because we can use the same parameters in many different locations throughout the model, and by that we'll be able to decrease the amount of the storage needed. So we have this input, and we don't have like for each one of these there we have different input. So now let's talk about the sparse connectivity. Okay, so the idea of sparse connectivity implies just a small number of units, okay, should be connected to each other. Okay, so we have in this illustration, we have x3 as an input image, and this x3 output units affected 3 hidden layers as. Okay, so you can see all these highlighted outputs units are affected by this x3. So x3 has affected s2, s3, s4. Okay, and by using sparse connectivity, that will allow us to turn a model that has a large number of units without having to learn many different connections. Okay, or we have something else which is called dense connections. Okay, well, in this case we have a dense connected layers, so you can see all of them, they are connected not like this, they are not dense, they are sparse. Yeah, so these are connected layers based on multiplication by a matrix. The connectivity is no longer sparse, as we can see here in this case, and our input x3 has an impact on all the outputs. So we can see that x3 can affect S1, S2, S3, S4, and S5 as well. So in conclusion, using sparse connectivity will allow us to turn a model that has a large number of units without having to learn many different connections. Okay, and we have another example. Let's say so we have another way of looking at sparse connectivity. So it's looking at one of the outputs. Okay, and one of the output and determining which units that have an impact for this output. So we can see that this output is like affected by x2, x3, and x4. Okay, so here SF3 is formed by convolution with a fixed kernel. So here the kernel size of 3. Okay, and each output unit will be only impacted by a fixed number of input unit. Okay, so we have a kernel of with the 3, and so only 3 input affects what our output unit, which is S3. Okay, here we have a similar button. If your layer is densely connected, as we can see here in the image, every output unit will be impacted by every input unit. Okay, so when S is formed by matrix multiplication, connectivity is no longer sparse. As we can see here, the connectivity is no longer sparse. So all of the inputs affects S3. Okay, not like we heard just like you have few inputs that can affect our output units. No, here we have all the inputs can affect our outputs layer, which is S3. So let's take a look here at this image. We have the respective fields. So if you have multiple layers, so as you can see here, we have, for example, like this, the first input layer, the second layer, and the third hidden layers. Okay, so your respective fields grows as you move one layer to the next. Okay, so in this example, like what we said before, we have an input X, and we have two hidden layers, which is H1 and G1. Okay, and we can see that every units in the hidden layer can only see, in this first hidden layer H, can only see 3 units in the previous hiddens. Okay, so H2 can see only X1, X2, X3, and as well for the hidden layer 2, for which is J3, can only see 3 layers in the previous one. Okay, but yeah, since like H unit sees a different, since like as you can see here, H units, we have different H units, the 3 of them can see different set of X units. So for example, H2 can see or affected or activated by X1, X2, and X3, and H3 as well, it's affected by X2, X3, X4, and H4 as well, X3, X4, X5. Okay, so since each H units see a different set of 3 X units, we end up with G3 seeing all the 5X unit. Okay, as we can see, we moved here and H3 was activated by 3 units, and like so on for H2, H3, H4, and the end. Yeah, so H2, H3, H4 will activate this output unit. Okay, so as you can imagine, as you add more layers, as you actually see more and more units, and one can end up with very large respective field. Okay, so let's take a look at this example. So in this example here, we have an image. Okay, we have an input image. So this is a dog with a kernel with size 2 by 1. Okay, And in the right, we have an image that was formed by taking each pixel of the original image, which is the input one, and subtracting the value of its neighboring pixel in the left, because we have one of them is positive and one of them is negative. So in the area with dark pixels, the negative one will be react, okay, while the bright area, the positive one will react. Yeah, and yeah, let's take finally we have this convolution neural network architecture. So this convolution neural network, it has an input image, as we can see here. It has 256 by 256 by 3, okay, and then we're gonna feed this input to our convolution layer, okay. So we're gonna put this one for our convolution, and like what we said before, sometimes we use the we refer for the convolution layer for using the convolution and radio at the same layer, okay. So we are gonna apply this convolution for 256 by 256 and 64, and yeah, based on that we are gonna take this the output of convolution and feed it to the boolean layer. For example, want to do downsampling, or to want to do max boolean, or want to do mean boolean, okay. And after that we'll do and repeat this several times until we like just get for that desired outputs that we want, okay. I will take our output and feed it into like a matrix, and then we have to apply like output of the softmax. For example, we have like different classes. Let's say for example we have 5 classes, and we'll take the which class that has the highest score, okay. So we have the deep learning is we have it has very well history. So for example, AT&T neural network research paper was created in a convolution neural network. So their main task was to do and perform a document recognition. You can take a look. So this was published in 19th, and after that Microsoft began developing this system in the field of handwriting recognition systems based on convolutional networks. And yeah, for example, we have another example that's in 2012, Convolution Neural Network was able to win the ImageNet Object Recognition Challenge. Okay, so I hope that everything was good, and have a nice day. Goodbye.